But yeah, we'll do a few questions now, and then we'll do a demo for IBM Composer if anyone has questions. We'll probably have time for 1 or 2 questions, short questions right now. And if you go ahead. Sorry.
Go ahead. In your timeline, you said in last year you had a processor with like 63 qubits, which I notice is bigger than the sort of famous Google experiment where they showed some supremacy. Has IBM been able to reproduce the types of results that Google got with their whatever it was 53 qubit machine? In other words, can you show that even that sort of not very useful quantum supremacy can be scaled up to, say, 65 qubits, your Hummingbird, or more?
They're different. So there's obviously lots of work and research being done on proving that, hey, here's Grover's, for example, shows a quadratic speed up. But Grover's, you can't really just pick up and use and throw it into an actual problem, right? To solve an actual problem. It's an example of something, just like most other algorithms that are there. So the work that our research team does is focus, and usually primarily why you're seeing a lot of these work with the different industries and different partners and members, is because we're actually working on trying to figure out how to solve an actual real problem, right? So our goal is to solve a real world problem. There's a lot of research going on proving, like, look, quantum can be quick here, quantum can be quick there, but when you get whatever that solution happens to be, or research, when you say, okay, now let's map it to an actual problem, that's where there isn't that direct linkage there. So all of our research, all of our work with our qubits and on our processors and our software and everything, as you saw, is aimed at actually working towards real world problems. That's why with the 150 plus members we're all working on just that. Like you mentioned, the Daimler is focused on batteries. We're looking at how do we create better batteries, not how do we simulate a battery that looks like it's how do we work towards figuring out simulating batteries. With finances, how do we look at fraud detection, what types of variables? You have software that does this. How do we find where the quantum would be optimal in these particular components, right? So it's just a differentiation. So it's not more of, let's look at a algorithm that somebody proved and let's try to see how we can make that a bigger thing. We're just going right to the end, in a sense, saying let's look for an actual problem that works. So I hope that answered your question there.
Great. Robert, could you throw that link that you had in the chat as well? Oh,
sure, yeah,
cool, you did that.
Yeah, I just saw that.
Okay.
Let me see, there's some questions here. So let me see, also the previous one. Are we able to throw? Oh, okay, no, yeah, I guess the other questions were from the previous discussion.
Okay. Yeah, if we can get started with the demo, that would be great. And then any questions after that could be just thrown in the chat.
Sure, no problem. Let me switch over to my browser here. Okay.
As a note to everyone, this is basically a second presentation. Robert is going to give us a demonstration of the IBM Quantum Compute Composer that you can actually go out to today, and I'm sure he'll go through the details of that. But if you have any questions, feel free to put those in the chat, or let us know.
Yeah, feel free to interrupt. I mean, I'm going to kind of be flowing through this, so no worries. All right, so sorry, so I posted the link in the chat. So when you go there, you'll probably ask you just like anything else, register. You can register with your email, with your Gmail, with your GitHub, various different ways you can log in. Pick your favorite, and once you log in, you'll enter this page here, which is your homepage or the dashboard, main dashboard of the IBM Quantum app here. When you get there, you'll see a few things. So obviously on here on the right, some recent notifications. So just news and things that are coming up. We have a new Qiskit textbook beta that's now open. I highly recommend if you're starting anywhere, definitely start with this. It's a great update. The beta is actually a lot more interactive. So unlike most textbooks you see online, it's reading, it's a snippet of code, and you got to copy and paste it, and some things don't work because it's missing, some libraries or something. The beta has everything already built in. So you run, you can click, it'll run it. You can see things actually happening. So it's a really, really great tool. So I highly do recommend going to it. But the rest of this, it gives you a lot of news around different things that are happening, different research that's coming out, system updates, etc. So it's a really good, just kind of get you up to speed. Here you'll see an API token. So just like any other service you use, when you want to install Qiskit locally and you want to use the hardware that you have access to, you just copy the API token, load it, save it to your local device, and that's it. Once it's saved, you just have to load it, but you never have to save it again unless you change it. And here on the left are the two different ways you can build circuits. So this one here is the IBM Quantum Composer. So this is basically a graphical UI to build these circuits. And this is actually ideal to use, particularly if you're learning, it's your first time. It has a lot of great UI components that you can use to visualize things, everything from the state of the device, of the qubit, if you take a measurement, what the probabilities would be, etc. So it's really good. And you can actually see as you add gates what it looks like. So I'm going to be going over that today as well. And also the Quantum Lab, which is in essence just a Jupyter notebook, but it already has all the Qiskit libraries and everything already installed. So if you just want to use it without having to install Python or anything on your local machine, you can go straight here and launch the lab, and it'll load up all the prerequisites for you, preload the libraries, and you'll be good to go. And I'm going to go over a little bit of this here as well. We're down here in the quantum services. So these are the actual different things that you have access to here. And some of them will show you systems that you have, like for example, your systems. When you log on, you'll automatically have access to some of the systems that we have available for free. Those are those 5 qubit devices. There's a device that's available for Pulse, which allows you to actually send pulse signals and define those pulse signals to those qubits. So you have access to be able to do that as well. So if you want to create your own pulses, you can. And of course, access to the actual quantum devices, as well as some simulators. There are different types of simulators, so you're not thinking it's just one simulator fits all. There are state vector simulators, there are unitary simulators, there are pulse simulators, there are COSM simulators, etc. So you can get access to those. And to view those, you can click this View All, and that will open up the view of all of the different programs you have. So you can see here's the different programs that are available: kernel, quantum kernel alignment, VQE, etc. If you want to look at the actual systems, which are the hardware, you click here, you can see that these are all systems. You see by this pull down. If I want to see what everything is available, we see at this moment we have 21 quantum computers online. So you can look online, see all the different devices. You can see there's different names. Now these names, is not where the quantum computers are. This is just the names of the quantum systems, just so we can determine it. Originally, we were naming them after a city where IBM had a research lab, but of course we had more quantum computers and research labs now, so we just started naming them after cities where there's an IBM office. So you can see there's lots of them all over here. And with the device, of course, you can see some information, the number of qubits that are available, the quantum volume of the device, what types of processors they are. This is the Humming 2, second version of that. The status, whether it's online. You can see this one is online, but it's a dedicated device, which means that if you're on the IBM Quantum Network and you have dedicated service, this is the system that you have. So you can see all of those different components here. And if you want to see some information about them, you can just click on it, and you'll get this little flyout that gives you some details about the device. How many jobs are waiting in line. In other words, these are how many people are waiting to run execute their quantum circuits, the basis gates, the error rates that we have on the devices, on the qubits. If you scroll down, you can actually see a visual representation of those. So here for the single qubit, you can see here the different ranges, and the average is right here. For the CNOT connections, you can see some of the error rates around here. And of course, it's color coded here as well. So you can see the darker is low and the purple or magenta is high. So you can see those differences here. So it gives you a lot of this information. And of course, you can always access them, and they try to calibrate this at least once a day. You can see this one was calibrated just 28 minutes ago. And if you click here, you can download all the details about the system, so you'll have access to that as well. And you can go through all of those here. You can look at the 65 qubit. You can see this one here, it's Brooklyn, and it has more information here, the type of system, and you can see here all the different qubits on the 65 and how the topology of how the qubits are connected. So you get a lot of good hardware information. So this is all the devices. If you want to see which ones you have access to, you can go here to your system. So this is the free ones. So I'm logged in as a free user. So these are the ones that are available for free. So you can see there's a whole array of 5-qubit devices with all different types of quantum volume from 8 all the way up to 32. And then we have this 1 qubit device here, which is used because we use these for the pulse to be able to do pulse actions on them. But I think right now you're able to do them all if I spread the last update correctly. And of course, simulators. You have all the different simulators you have. Like I mentioned, there's more than one simulator, type of simulator. So you have a Cosm simulator. This is just general, it's context aware. That's the type of simulator it is. You can run up to 32 qubits. This simulator is actually running on a Power 9 server, which has a lot of resources, a lot of memory. So you can definitely run up to about 32 qubits before it really starts to get you reach that peak of what you can run on the device. You have a simulator extended stabilizer here for Clifford. 63 qubits for that, a similar MPS, which is a matrix product state. So if you're running matrix operations, you can use this one. You have a Clifford simulator you can run here. You can run that, obviously it's up to 5,000 qubits, and the Schrodinger wave function for the state vector, and that one you can run up to 32. So you have different types of simulators you can run these particular devices on. Now, so going back to our dashboard, now if you want to use it, if it's your first time learning quantum computing, I definitely recommend a composer. And to launch that, you have a button here. You click launch, and what that will do is it'll launch this particular UI. So I'm going to minimize this left layout and give you a little tour here. So here you have the circuit. So across the top, obviously, just like anything else, you can open up details, any recent files you've had. You can edit certain components of it. Inspect is just that. You think of it as a debugger in a sense, or inspect like you would inspect any application. You can step through your code, and as you step through, you can see how the code changes, and we'll go over that in a minute. And then you have views for your different views you can see. So I can see here my state vector, my Q-sphere, which is a 3D representation of my circuit. And if I want to add another view, there's a probability. So this is if I want to take a measurement. Remember, as we learned earlier, when the quantum is at a particular state, it's in a quantum state, because you're running on a quantum system, it doesn't read 0 or 1 on classical computers. We have 0 or 1. That doesn't have a combination. So it will take a measurement, which means that that particular vector will collapse to either 0 or 1. And based on our probability, we'll see that here, right? So right now, because every qubit starts with, let me clean this up a bit so it looks a little bit easier for everyone. We have the initial state for a qubit is always in the 0 state. So you can see here our state vector shows that we have a state 0. The amplitude is 1. The amplitude runs between 0 and 1. And we have no phase angle. We haven't done any phases on this thing yet. On a Q-sphere, we can see here by the vector that the north pole of this Q-sphere, it's the 0 ket. In other words, the ground state or the 0 ket value. And to the south pole is 1, right? The 1 ket or the excited state. The ball, the edge here, it's blue, meaning if you look at this color phase wheel here, which means that we haven't done any phase changes, so it's in phase. It's at 0, and the diameter of the edge here of the tip is at full, meaning it's 100% here, right? So it's showing that there's a 100% probability. Now, so this is for a single qubit, and of course our probability means that if I take a measurement, I'm going to measure 100%, that it's going to be 0, because obviously I haven't done anything. If I just measure this and run it, I'm going to get a 0. Now, of course, you can do the same thing on classic circuits as you can in quantum as well. Rather, quantum you can do it classic. So here's a NOT gate. So if I start at 0, if I drop this in here, you'll see that everything is going to update. And now my state vector is at 1. So my amplitude is at 1 because I'm in the state of 1. I flip this. You can see the Q-sphere also move from the north pole to the south pole here. And I have a state here of 1 with a probability of 1. And here's my probability as well, 100% that it's going to be 1. So if I take a measurement here, it's a 1. And of course, just like classic systems, if I put another NOT gate, that's going to reverse that. So it's going to bring it back to the 0 state.
So Robert, real quick. So you're saying that you guys initialize your qubits at 0?
Yes.
And then you can just place those gates down and try out different possibilities?
Correct. Exactly.
Awesome. Yep. Okay, cool.
Yep. And also, as you'll see here on the right, this Qiskit view, this will actually updates the code, Qiskit code. So you can see here where it's importing some of the very generic, at least most of the objects and functions that you normally would use, and it creates this. You're creating a quantum register of 1 calling it Q because that's why I only have one qubit and I give it the label Q. I have a classic register calling it C, and it's only one, which you can see here as C1. And I'm creating a quantum circuit, which is basically grabbing that quantum register and classic register putting together, which is what you see here between the two. Now, so you saw what we did with NOT. As you do this, all my views update. So now if I want to get into the quantum side of things, let's drop a Hadamard gate. Now, a Hadamard gate is the name of the gate that puts the qubit into a superposition, which we've learned about earlier is a sort of a combination. It's actually a complex linear combination of the two. Needs to be a more formal definition of it. So you can see what we're looking at here now. Our amplitudes are now equal. I have an equal amplitude of 0 and the same amplitude as state 1 of 0.707. The phase is still 0 because I haven't gone out of phase. It's still, I just moved it down into between the two. You can see here in a Q sphere now though, that the state of 0 is at a probability of 0.5, as well as the state of 1 is at a probability of 0.5. And that, of course, is because I haven't, we have moved any phases and it's just equal probability. Now, because it is, you can now also see that the diameter of this, of the tip here of the vector is now smaller. It's about half the size because now out of that 1 that it was before, it's now sharing that probability between the 0 and the 1. So you can see it shows you a visual representation of that. And of course, the probabilities, when you take a measurement, if I run this once, there's going to be a 50% probability my resulting state will be 0 or 1. So if I run this once, it's going to be one of the two. If I run it 100 times, I'll probably have about 50% going to be 0 and 50% of my results will be 1. So this Hadamard gate puts this being in a superposition. So when I run my experiments, yeah, I'm already running in both states in a sense, right? So these are, so this one here is a Hadamard gate. These dark blue one, the colors of these basically are represented. Now, if you hover over this information bar, it kind of gives you a legend of what those mean. So the orange one is the Hadamard gate. It's the only one that we have that puts in superposition, so it has its own color. The ones in blue are classical gates, meaning that those are not, they don't have any quantum functionality. We saw the NOT gate, which is the first one. The second and third one you see here, these are actually what's called a control NOT gate. And what that basically means is that when the target or the control, which is 1 qubit, is enabled, and if the value is set to 1, it's going to enable the target operation, which in this case is the control NOT. It's going to turn on that, enable that NOT gate on the second qubit and flip it if it's on. If it's not on, then it won't do it. But this is a swap gate, so it swaps the information from 1 qubit to the other. And this, of course, is an identity gate, which is like a buffer gate in classical systems. It just doesn't do anything. Doesn't do any operations on it. So those are the classic gates. Phase gates now, these are just that. So when you put something in superposition, it's basically within 0 and 1. It's in some probability, some area between the two. What you can do with phase gates is that now I can apply rotations around those particular pieces. So you can see here between 0 and 1, I have the phase is equal to 0. Right, and we can see, in fact, let me enable this. It might be small, but you can see a 0 ket with 0, and the 1 ket has a 0. Now 0 here is determined by the color blue as well. And you can see this is a sort of a color wheel here for the phases. So if I rotate this particular qubit to the pi gate, pi, which is a Z rotation, I can grab that gate here. This is my phase gate, a Z gate. Z gate basically rotates at pi around the Z axis. So if I bring that down here and let it go, you can see now things change. So from the 0, there's no phases on the 0 component. It's just still blue, so it's still in phase. However, the state of 1 is now out of phase by pi, and that's at 0.707. At 0.707, it's 1 over square root of 2. Just so you know what that means. So when you see earlier when you saw, I can't remember which presentation it was where we were seeing the different states of superposition. It was the 0 ket plus the 1 ket over the square root of 2. That's what this is. The square root of 2 is the amplitude.
So Robert, I guess just a way to think about that then, would this be a good way? We have that sphere that we kind of saw, the block sphere, with those different possibilities between 0 and 1. Right. And so with the phase change, is that basically changing it to different areas around that axis?
Yeah, in fact, here, I just realized I had my camera off and I was doing all these things with my hands that you guys weren't seeing. So sorry about that. So if you look at it from a block sphere perspective, so if you hold your thumb up in the air like a thumbs up, this is the 0 vector, right? And if you rotate it down with thumbs down, that's the 1 ket, right? There's the 1 vector. Now, a superposition is basically putting it right in the middle, right? So if I just rotate it this way, I'm in the middle between 0 and 1. but I came down on this particular angle. So I'm at 0. I'm not in phase. So I just went, that's what the first step we see here, the Hadamard, that brings us to position. Now, if I rotate the Z axis, I'm now pointing to the negative direction on this thing, right?
Okay.
So now I'm out of phase by pi, as you can see in the wheel. That's why the 1 is red, because it's indicating that this is pi, it's out of phase by pi. And so that gives you that differentiation. Of course, that helps you get those negative values that you're reading about, things like phase kickback, which we don't have time to cover now, but
Right.
very important.
Yeah. So I just wanted to highlight that a little bit, just for the audience members. You know, those gates there, it sounds like what you're saying, Robert, like those are the kind of the how you create those more complicated and complex algorithms.
Yeah, in fact, so Z, and each one has a different angle. So these are preset, right? So Z is pi. S, if I drop it here, it's pi over 4. So if I do that, you'll see that the 1 is almost pink. And if you look at the wheel here, it's pink. And if I hover over, it's pi over 2 here. And if you look at we'll go back here, cut this and put the T gate in here, that's half of that. So this is going to be pi over 4. So if I come here, it's pi over 4. You can see it by the phase angle. You can see it's down here in purple because that's more or less from magenta. That's where we are. So these are preset, and the daggers are just the same gate in the opposite direction. So if you recall, we did S, which brought us to pi over 2, which is in magenta. But if I get the S dagger, it's the same angle, but in a different direction. So this is going to be yellow or yellowish, because it's coming a pi over 2, but in the opposite direction, which is 3 pi over 2, which is that yellow. So these are sort of preset type of rotations, but you can, of course, rotate. You can have this RZ gate, where you can then say, okay, I want to rotate it, but only certain degree, by a certain amount. And that was earlier what I think, I don't know if it was John or someone was talking about, you know, when you put these angles, you can specify when you're entangling that random, I think it was, it might have been Sean, we was talking about you get random numbers, and you have 0.63. So you can rotate Z in a certain way where it represents 0.63. So this is what's referred to as amplitude encoding in quantum. Right? So I'm encoding these amplitudes at a certain amount, a certain rotation, and that will basically help define that problem, right? And represent that information into the quantum state. So you could do those with these phase gates, as well as you can define your own gate. And now one thing also to notice, and I want to make sure I mention here, is that as you're adding those circuits, you can see here that the code actually updates. So if I drop a Z gate, you see here it has the H gate on my circuit. But now if I add a Z afterwards and I drop it here, you can see it adds another line and adds the Z. So you can watch and learn how to code it at the same time as you're learning how these things operate. So this, like I mentioned, this is a really great tool, at least to get started. Now, obviously, this is 1, 2, 3, 4, 5 qubits you can play with, but if you're now coding for 1 million qubits, you're really not going to use this tool. It's going to be very difficult to manage your algorithm. So with that, that's why I don't use that last minute to kind of cover.
Real quick, I just wanted to point out a few things, because I know for people who are going to work on this, I know when you something that I found helpful, if you go back to that previous page.
Oops, that's a lot. I should have went to the, my bad, composer.
Yeah, I just wanted to quickly show something that I found valuable in there is under that little I with the information. I think you guys have for the gates. I think you have an operations. Actually, on that information, you guys have a operations glossary.
Yep. None. Oh yes, not here. Yeah, correct.
Yeah. So I think this I think shows the different gates.
Yeah. Yep.
In what they do.
More detail. Yeah, this gives you more detail. So, for example, let me go to the Hadamard. If I can just click on it here.
Yeah. So this, I think, and from what I saw before, this kind of helps if you're trying to bridge the math behind this with the gates. This glossary I found very helpful for myself to kind of see, okay, when you look at the linear algebra that defines all this, how does that play into each of these gates? I know that glossary can be helpful to look at. Another thing is that the Qiskit textbook that Robert mentioned earlier has a lot of demonstrations of how you can do this in the composer, and I think in the Python. Anyway, Robert, I'll hand it back over to you. Maybe if you want to spend like a minute or two. I know I took a little bit of.
Yeah, no, this will be quick. I was just calculating for a minute, so no problem. So this last component, so the quantum lab, In fact, here, let me create a new one so that we can, so I'm gonna create a new lab. This is something I was working earlier. So when you go into a quantum lab, what's like I mentioned before, quantum lab is a Jupyter notebook, but it already has everything pre-built in there. So it has everything installed. If you want to run things locally on your device and not connect to the cloud and just run things on your machine, you can install Qiskit locally. If you have Python and Jupyter notebooks or whatever editor you like to use for Python, you can do that, no problem. Now, when you want to, once you do this on the lab, it not only has it installed, but it also, you can see this has this boilerplate cell that it creates, auto generates, and it basically just imports a lot of the more common classes and functions that you use to generally run a quantum circuit on a quantum device. So it has all those things in there. One thing it does have, and I will stress this as well, because we usually get a lot of people asking the question, when you install it locally, you have to, as I mentioned before, you have to first save your account, your API token on your local device. And then before you run a notebook that you're going to run on a quantum system, if you're going to run it, if you run it on a simulator locally, you don't have to do this. But if you want to run it on the actual device, on the actual quantum computer, make sure to run this line here, or you can call it whatever you want. I call it provider because that's just how they do it in the textbook. But you want to load your account, because when you call that way, it knows that which user you are and what devices you have access to. So once this is loaded, then you can just start coding up. You can start actually creating a quantum circuit, run those things. If you go to the quantum textbook, in fact, and I have it here, you have some tutorials in the API documentation. So if you go to API, let me actually copy this in there for you all.
You know what, Robert, I'm sorry. I don't want to steal any time away from Shuai for him to get started, but I know there's a lot of great information on that on those two websites that we posted in the chat. Definitely check those out. A lot of excellent. Just I would really encourage you to play around with it. It's a really good way to get some of those basic fundamentals figured out. With that, if you have any questions, go ahead and post in the chat. And Robert, I assume you can take them from there. Shuai, if you want to go ahead and start sharing screen, I'll let you get started.
Great, thank you.
And just a note to everyone, Shuai will be our last presenter for the evening. So if you guys can stick with us, I know he's got some good stuff to share, and we appreciate that, Shuai. Thank you.
Yeah, sure. Can you see my screen?
Yep.
Okay, great. All right, so thank you for inviting me for this talk, and also thank you for the Sam, Robert, and Chris talk. So they are talking about something quantum, real quantum thing, transfer everything from classic to quantum. So unfortunately, I'm going to talk about something which is a kind of dequantized. I'm going to transfer the quantum to classic. So I hope you will not hate me, okay?
Just as a note, this is definitely valuable stuff. If you're looking for some of the benefits you can get from quantum now, this is the kind of stuff that to look at. So sorry, go ahead, Shuai.
Thank you. Yeah, so my talk is about the quantum-inspired algorithm, and we're gonna have 4 parts of my talk. So the first one, I'm gonna talk about the general quantum and the dequantized algorithm. So the quantum computing has the potential to revolutionize the information and the communication technologies. And one of the most promising area is the quantum machine learning. And recently, the many quantum algorithms with the potential speed up were proposed. For example, here I'm listing many quantum algorithms for the machine learning. And all this machine learning, quantum machine learning algorithm provides exponential speed up compared to their corresponding classic algorithms. So that is a very, very huge jump, at least for time complexity. It's a very huge jump from classic to quantum. And in this presentation, I will focus on the dequantize the quantum machine learning, quantum algorithm, machine learning algorithm. So based on the Evan Chang's breakthrough result in 2019, so which means I'm looking for classic sketching algorithms in a quantum inspired model that mimic quantum algorithms. So in other words, I'm going to introduce a sampled query exercise model as a classic analog to the quantum state preparation assumption. Okay, so the first thing I'm going to do before we introducing what is a quantum inspired model, I'm going to say, let's see why we need this quantum inspired model, why we want to kind of dequantize some quantum machine learning algorithm. So they are fantastic algorithms. They're brilliant. But why we so at least right now, why we still interested in dequantize them? Okay, so this most likely because of this it's called strong assumptions in quantum algorithm. We call it state preparation assumption. So this state preparation assumption is usually being used for most of the quantum machine learning algorithm. Usually quantum machine learning algorithm abstract away this implementation details, assuming a number of desired quantum state already prepared. But unfortunately, this preparation procedure is non-trivial. So if you're using the amplitude amplification trick, this will require time at least a big O square of n, where n is the number of input vectors, to generate the quantum vector state category. So in general, this in general. But of course, I mean, I think in several years ago, the people from I remember from MIT or from UC Berkeley. So they give another result that for some sparse vectors, it may the time complexity may be reduced. So it can be only depends on the number of non-zero elements, the time big O square root of a number of non-zero elements. But still, so the data structure to quickly prepare the quantum state is essential for the quantum algorithm to achieve the query complexity polylog in the input size. Remember, all this previous quantum algorithm, they can achieve the polylog time of the number of input vectors, which is exponentially faster than any classic algorithm. But if you are thinking about this state preparation assumption, so that will take you a lot of time and will dominate the total running time. So inspired by this one, so we are giving, not we, I mean, so this this norm-based sampling model already being used for many machine learning algorithms. But here we're gonna see how a classical algorithm can perform as well as a quantum algorithm. So the key observation here is that the data structure using to satisfying the state preparation assumption can also satisfying the norm-based sampling assumption. I will come back to this later. What is a norm-based sampling assumption? But so far, I want to say that is the key observation for this all this works. So in impressive sense, quantum-inspired algorithm replace the state preparation assumption with this norm-based sampling assumption. It makes the quantum input-output oracle to classic input-output oracles. So for any quantum algorithms, we are preparing the copies of the cat-way, which is the quantum input, and we running this quantum algorithm. Then we have this quantum output in superposition or something, and then we measure it. We get the sense. But we want to do this one classically. So that means we want to do something like a classic input and classic output. Okay. So in other words, so instead of the strong state preparation assumption for the quantum algorithm, we will also put assumption in classic algorithm. Okay, so we still have some assumption, but it's a mild assumption, but it's more realistic than the quantum assumption so far. Okay, of course, when we have a stronger, powerful quantum computer, the problem may not exist. But so far, we still put some assumption in the classic algorithm, which is performed much better than quantum one. So it can be easily implemented in the classic computer, and the current quantum state assumption, both hardware and software, is not yet ready for implementation of some complex machine learning algorithms. So let's see what is a norm-based sampling. So which is a core part of the quantum-inspired model. So if you're given an n-dimensional vector x, and we will define a distribution over this vector x by this probability will be xi squared over the norm of the x. So that will be how we define the distribution. So that means the heavier of the entry weight, the higher probability you will have in this distribution. Okay, so I see some questions in the chat window. Sorry, I probably, yeah.
No questions yet.
Oh.
Just a note, Shuai, it sounds like you might be bumping your mic occasionally. Just an FYI.
Oh, what's that? Sorry, I cannot hear it.
Oh, I think you might be bumping your mic occasionally.
Oh, really?
Heard a little bit of that. So
Okay.
just as a note.
Oh, okay, thank you.
All right, thanks.
Yeah. And okay, so we're talking about this norm based sampling. Okay, so once we have this norm based sampling assumption, so we have two important facts about this distribution. So the first fact will give us the corresponding between its classic sin and the quantum sin. So that is look at this distribution. This distribution resulting from measuring the quantum state cat x. It's exactly the same as we do the superposition. We put the x into different coefficients and do the linear combinations here. So that is exactly reflect the probability when you do a measurement on this quantum sense. So that's the same thing, but it's become to a classic distribution in classic computer. And the second thing is, if we have this sampling access to this distribution, that will make many tasks very easy compared to the regular only query access to this vector. So for example, if we have a vector and we want to find the largest entry of this vector, okay, so if we only have the query access like our classic regular RAM computer, so we will, the worst case will be we have to scan the whole vector to find the largest one, maybe in the last position. So the running time will be running something around big O n, right? So it depends on the dimension of your vectors. But if we're giving this a sample and the query access to this vector, just like the assumption we did here, if we have this non-based sampling, so if you have a very large entry, so you only need to take the constant time you can find it, right? Because if it's very large, they will corresponding to a very large probability. So when you query is sampling from its distribution, usually big O series, big O one, so just constant time you will find it. So that is a very simple example showing how why this is so powerful to do, why we need this sample and query exercise. And also this is the core part of this quantum inspired model. Okay, so assuming this is a sample and query access in the quantum inspired model, that means if all its input vectors or the matrix, we can build such a kind of norm sampling based distribution or it's a data structure. So we're gonna do some very fundamental mathematical calculations or computations very efficiently. Okay, so first thing will be the inner product. So we can estimate the inner product, not exactly, estimate the inner product of two vectors very fast. And the amazing thing is it will be independent of the vector's dimension. So it means no matter how big it is your vector's dimension, so we can do it in this time. So you can say the running time, the time complexity only depends on the successful probability and the additive error. So will be nothing to do with your dimension. But for regular query access RAM model, so you will do this one, of course, with some linear. Right? So you have to do, depends on the dimension of your vectors. But once we assuming this sample access, we will not, the time of complexity will be independent of this dimension. So the second one we're gonna do is a linear combination of the vectors. That means we are giving a collection of the vectors. We can estimate the linear combination of them efficiently. So in other words, you can also see if you treat the collection of these vectors as a matrix and the linear combination as a matrix multiply another vector. So you can see this one, the linear combination of vectors is a matrix multiplying a vector. So this can also be done efficiently. And here is the time complexity for this one. And it's only, again, it's not independent of the dimension, but will dependent on the norm of these vectors. So this can be proved by using the rejection sampling instance. Okay, so within these two very basic fundamental things, we can do something non-trivial, which will be a very important or core parts of many, almost all quantum-inspired algorithms, which is the approximate singular value decomposition, SVD. So that is for any matrix A, we can decompose as U times sigma times V transport, which is a singular value decomposition. So that is very important for many machine learning algorithms. And for such kind of a procedure, if we have this distribution, we have this data structure, we can do this one in a the classic SVD will take at least a quadratic time or cubic time, at least quadratic time, I think. Okay, so that is basically why we need this model and how powerful it is. And as you can imagine that once we having this such a fundamental mathematical tools and we can do such a fundamental mathematical computations, we can do almost everything we like to do, right? And here will be example. Okay, so that is called we will dequantize the quantum slow feature analysis, and this quantum slow feature analysis is by Karinides and Logo in 2018. I think some of you may be very familiar with Karinides, right? He's a research scientist in the QC Ware. So he and Logo provided this quantum slow feature analysis in 2018. So, but unfortunately, we're gonna dequantize that. Okay, so briefly speaking, so for the slow feature analysis, as its name suggested, oh, sorry. Okay, as the name suggested, it is an algorithm for extracting the slow varying features from a fast varying input signals. The ability to find the time invariant features allow us to identify the characteristic of the environment. Okay, so we can intuitively thinking that this is for example, you have a child, you have a signal of a child. The child is jumping up and down very quickly. So the visual signals we receive are rapidly changing because they're jumping up and down, and the image ends up blurry, right? Because they're jumping too fast. However, for most people, we can just use our eyes to, there's no trouble to recognizing that is this blurry object is in fact a child, right? But how are we gonna do this one in a machine? So we have blurry pictures input for a machine. So how are you gonna do as what we are doing in our eyes? So that is a kind of, we have to, the slow feature analysis will help us to extract those features that change slowly, or sometimes feature does not change, which will help us identifying this object. Okay, because of this property of the slow feature analysis, people also using this slow feature analysis for classification. Okay, so to capture the slowest varying features will give us another view, another way to do the classification problem, which is also online classification problem. That means every time you give a streaming input signals, it is very easy for this slow feature analysis classification to classifying it. Okay, so let's see. I'm gonna see what is introducing the high level idea of this slow feature analysis for classification. So the first thing we're gonna do is for any input vectors will belong to one of the k different classes, where k is the number of the clusters you want to classify. And then the goal of this slow feature analysis for classification is to learn k-1 different functions, gi, and such that these functions will project the input vector to a lower dimensional space. Sometimes we call it a slow feature space, such that when we compress the data set, it will make the data set very similar inside of each class, but a very large difference for the different class. So it's kind of you bump this the gap. There's some gaps between some clusters, but after you're doing this kind of compression, so you'll make your gap bigger. And once we learn these functions, that means we can compress data in a good way that can make it to be make the different clusters that's bigger and bigger. Okay, so then when we have a new data point that arrives, we'll map the vector space by using what we learned is the k-1 function gi, right? Which will help us doing the classification be done with higher accuracy. Okay, so that is the high-level idea of what you're going to do with slow feature analysis. And of course, it can be transferred into a formal mathematical problem, which is many details here. So I'm just skip it, and I will say that this one can be transferred to be an optimization problem. That is for this kind of this function, the goal of this classification is the same as minimize this, you can say it's a cost function. It's similar to the cost function for regression or something. It's like a cost function for this slow feature analysis classification one. So our goal is to minimize this one. Okay, so so to minimizing this one, Kubernetes and Logo would give a quantum algorithm for that, but due to the time sense, I will not show it here. But here is our quantum-inspired algorithm, which is dequantize their algorithm, quantum algorithm, to be classic algorithms. So for these algorithms, there's many definitions here. So I will just skip it, and we'll talk about the high-level idea of this algorithm. So basically, there's two major steps in this algorithm. So the first one is called they call weighting the data. That is, when you have the input data, we're gonna kind of normalize or weighting here. It's called weighting to make the original problem to reduce to a normal eigenvalue problem. That means to minimizing that problem, to minimizing that function. If you do the weighting first, it's equivalent to say we're gonna find some of the eigenvalues of some matrix, some special matrix. Okay, the second thing is they call it projection in slow feature space. But actually it's just performing the principal component analysis on this function to find the first, so the k-1 lowest right singular vector of this z dot. And actually it's the same as find the smallest eigenvectors of the z dot transport times z dot. So which will call the k-1 smallest eigenvector, their spanning space will be our slow feature space. And everything, when you compress your original data to this slower spinal space, will give you the most like slowest varying features. Okay, so yeah, so that is basically the idea of this algorithm. So the conclusion is we give suppose if we assuming that the quantum inspired model, we're gonna give a sublinear time algorithm for slow feature analysis, for classification, especially this algorithm is the classic algorithm. But it is still slower than the quantum one. It's still slower than the quantum algorithm, but it is exponentially faster than any classic slow feature analysis one. Okay, so it's slower than the quantum, but for any classic one will be exponentially faster than that.
And since it's classical, it can be used today.
Oh, definitely, yes. And I think that last year there's a group of people in my MIT, they're doing this one in Python and they tested it for a little bit. And right now, one of our students, of weapon students, and he's trying to do writing everything in C language. We're almost done with that. So we're gonna test it in the C. So yes, definitely that can be done in a classic computer. Excellent.
Yeah, so I know we only got, that kind of dipped a little bit into our question time. I'll go ahead and take one question. If anybody else after that has questions, you know.
I'll put my, my contact information here. So if you have questions, you can always email.
Excellent. Yeah, if you want to put that in the chat, that would be great.
Sure.
Because I know you had a lot of details in there, and I honestly, yeah, I don't think that 1 minute's gonna do any of these questions justice. But Shuai has put his email in the chat, so you can reach out there to him and follow up on this. I know you got a lot of good stuff, and I think what's awesome about this is that the process of dequantizing, of just using of thinking about stuff from a quantum perspective, is that it can give us advantages today by thinking outside the box when it comes to classical algorithms. And I think that's one thing that your presentation really shows. On this note, I'm going to go ahead and close up, let everyone end for the evening. I do want to give just a thanks to the teams from our different speakers. Mindy Barrel, she was fantastic with putting us in touch with our professors from CASE and helping run some of the promotion on this. Also, thank you to our team at the team at IBM. Let me just, let's see, Jason, I don't know if I'm saying Daglewitz, and Yanni Gomvros from QC Ware. Great guys to work with, and yeah, they've been very instrumental in helping, helping make this a possibility. As far as for our next meetup, we're probably going to do something like this in January. It takes a little time to put together a speaker lineup, but we're really excited. We'll start putting that together, and we're hoping maybe to get Cleveland Clinic to discuss their plans for adding IBM's computers to at their clinic, which is going to be just awesome for the region. So. Also follow up.
Sorry, I forgot one more thing that I want to quickly introducing my students, Daniel Chen here. He's the first author of this paper, and he's an undergraduate student at Case West.
Fantastic.
He's one of the best undergraduate student in our school. So yeah. So Daniel, yeah.
Yeah, which is I think awesome just to see the talent that that we can bring to the area. So something for everyone to think about. If you know somebody who you think is going to be interested in taking some of the courses at CASE, definitely look into that. Other than that, like I said, we are going to put out the video recordings for this on the Meetup group website as soon as possible, and assuming there were no technical difficulties during that. We're also going to be publishing out resources, just a resource list for people to look at to get more details. I know people come at quantum computing from all stages of the learning journey, and we're really excited just to keep promoting this conversation, and we look forward to seeing everybody in person next time. So thank you so much, everybody, and thank you to our speakers. You guys were fantastic.
Thank you, Austin.
Thank you.
All right, with that, I'll give you 3 minutes back to your evening. And yeah, all right. Thank you all for coming. Appreciate it.
Thank you.
Thank you, Austin.